Questions? Obviously, you must have questions. Well, since Michelle was the first one here this morning,
In section 3.3,
okay,
number 9 and number 12.
okay. 3.3, 9, and 12. Okay. Prime factorization of 13 factorial and 27 factorial, and that'll lead to number 12. So even if you didn't ask 9, 9 is very good practice for 12. So we want the prime factorization, and let's see, which two numbers were they? They were 13 factorial and 17 factorial. And other one was 27? Okay. So what we're going to do is we're going to look at where 13 factorial comes from and pull out the various primes. So in particular, it's 1 times 2 times 3 times 4 times 5 times 6. Okay. So there's the factorization of 13 factorial, but not the prime factorization, but basically where 13 factorial comes from the definition. So if we look at the prime factorization, the only primes that can possibly occur are less than or equal to 13. So we know that the prime factorization of 13 factorial is going to be 2 to a power, 3 to a power, 5 to a power, 7 to a power, 11 to a power, and 13 to a power. And then we just have to go back and collect the various primes that occur. So 1 doesn't have any primes in it. 2 is 2 to the first, so this contributes a 1 over here. 3 contributes a 1 over here. The factorization of 4 is 2 squared. So 4 contributes 2 copies of 2. So 4 contributes an extra 2 to this exponent. 5 to the first power gives me a 1 over there. 6 is 2 times 3. So 6 gives me an extra copy of 1 and an extra copy of 3. Seven is simply 7 to the first power. So this gives me a 1 over here. 8 is 2 times 2 times 2. So that gives me 3 extra 2's in its prime factorization. So my box needs to be a little bit bigger here. 9 is 3 squared, so that's 2 more copies of 3. So 2 more 3's. 10 is 2 times 5, so that's 1 extra 2 and 1 extra 5. So an extra 2 and an extra 5. 11 is just a single copy of 11. 12 is 2 squared times 3. So that's 2 more 2's. And 1 more 3. And 13 is just a single copy of 13. Now, having shown you how to do this one way, I'll actually show another way. Now, my screen is blank, but I'm sure that's a screensaver, so let me just check that the whole recording is still going. Yes, the recording is still going. Or so I think. Let's check. Yep, still going. Okay. So when I add up the exponents, I get 2 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. People get 10 here?
Yep.
3 to the, that looks like a 5. 5 to the second, 7 to the first, 11 to the first, 13 to the first. Now, So one way to do it, and again, I'll show you another way. You should do whichever is more comfortable. You write out the product of all the numbers from 1 to 13, and then you systematically, for each of the factors here, take its prime factorization and see the contributions it makes over here. Another way to do it is, instead of taking each term in the factorization of 13, take each prime and we can separately compute the exponent of each prime. Now, this might not be the most expedient way to get the prime factorization of 13 factorial, but I think later on we want the number of zeros at the end of a factorial. This is actually a bit more useful for that because for those, you only want the prime factorization of specific primes. So what you can do is, and here's the little trick, to find the exponent of 13, you start with 13 and divide by 2, and the biggest whole number that goes in is 13 divided by 2 is, what's the biggest whole number? 6 plus something. What that means is 6 of these numbers are multiples of 2, because every other number is a multiple of 2. So 2, 4, 6, 8, 10, 12, that's 6 numbers. Each of them contributes a 2. However, there's more to it because some of them not only contribute a 2, but like numbers 4, 8, and 12 also contribute an additional 2 because they're multiples of 4. And 8 contributes another 2. Well, here's the procedure we do. We start with 13, divide by 2. We got 6 of these numbers are multiples of 2. But then you take this and divide by 2. That says 3 of these numbers are also multiples of 4. So that gives you an extra 3 copies of 2. Then you take this number and divide by 2. That's going to tell you how many of these numbers are multiples of 8. So you take this and divide by 2. It's 1 plus, again, at each point you just take the integer. So this says only one of these numbers is a multiple of 8. That gives you an extra copy of 2. So if you do it this way, when I multiply the numbers from 1 to 13, 6 of them are multiples of 2. Of those, 3 of them also happen to be multiples of 4. They give me an extra copy of 2. Of those, one of them happens to be a multiple of 8. Notice the exponent obtained differently, same thing. If you want to do this for 3, and as the primes get bigger, this gets much, much quicker to do. Let's move to the next prime, which is 3. If we start with 13, and we divide by 3, you get 4 plus. That means 4 of the numbers are multiples of 3. But take this number, divide it by, in this case, 3. That means one of these is also a multiple of 9. So that gives you an extra copy of 3. And again, once you're dealing with a number that's less than 3, you don't have to go any further. So this means that when you look at 13 factorial, 4 of these numbers are multiples of 3, and of those 4, one of them is a multiple of 9. That gives you yet an extra copy of 3. Notice the exponents match up. If we're looking for the exponent of 5, we take 13, divide by 5, we get 2 plus. In other words, 2 of these numbers are multiple of 5. Now we basically want to see how many of them also have to be multiples of 25. Well, the answer is going to be none, and you can check it from here. 2 goes into 5, the biggest whole number is 0. And now you can see as you go for the bigger primes, 13 divided by 7 is 1 plus something, right? So from here, there's one multiple of 7. So again, 13 divided by 7 is 1 plus something. So there's one multiple of 7. But since this is less than 7, there are no multiples of 7 squared or 49. Similarly, when you multiply the numbers from 1 to 13, you can take 13 over 11. One of them is a multiple of 11. None of them is a multiple of 11 squared. Only one of them is a multiple of 13. Do you have a preference which way to do it? I don't particularly know which one is quicker, but okay. So again, you can do it by, so again, technique number 1 is, for every number along the way, look at its prime factorization and look at the contributions it makes to the prime factorization. Or for each prime separately, do this little trick of how many of the numbers are multiples of 2, from those how many of them are multiples of 4, of those how many multiples of 8, similarly for here, how many of them are multiples of 3, of those how many multiples of 9, etc., etc. So, questions for 13 factorial. Since the second technique is going to be more useful for Michelle's second question, which I think was number 12, let me stick to the second technique. So, any questions on the prime factorization of 13 factorial? So for 27 factorial, the only primes we have to deal with are primes that are less than or equal to 27. So we're going to have to deal with 2, 3, 5, 7, 11, 13, 17, 19, 23, and that's it, right? Those are the only primes less than or equal to 27. So when you multiply all the numbers from 1 to 27, we'll do the same thing before. Let's see what the exponent of 2 is. If we take 27 divided by 2, that says 13 of them are multiples of 2. But of those 13, how many of them also happen to be multiples of 4? Of the multiples of 4, how many of them also happen to be multiples of 8? Divide that by 2. Of the multiples of 8, how many of them also happen to be multiples of 16? And once you're smaller than the number that you're dividing by, you don't have to worry anymore. So, if you multiply all the numbers from 1 to 27, 13 of them are even. Of those, so they all give you at least one copy of 2. 6 of them happen to be multiples of 4, so they give you an extra copy of 2. But of those, 3 of them are multiples of 8, so they give you another multiple of 2. And one of them is a multiple of 16. So if we add 13 plus 6 plus 3 plus 1, that adds up to, is that 23? So the exponent of 2 is 23. Next, for the exponent of 3, for the exponent of 3, 27 divided by 3 is just a straight out 9. So that means 9 of them are multiples of 3. Starting with the 9, 3 of them happen to be multiples of 3 squared. And taking the 3, one of them happens to be a multiple of 27. So when you multiply all the numbers from 1 to 27, 9 of them are multiples of 3. Of those, 3 happen to also be multiples of 9. And of those, 1 also happens to be a multiple of 27. When we add them up, we seem to get 13. And again, it's somewhat of a check. The exponents that you get here, like 23 followed by 13 followed by something, that sequence can never bump back up. Because each time you're dividing by bigger primes, so you're going to be getting smaller numbers. So again, the numbers you're getting here, if you ever sort of jump up, you know you got a problem. So, the bigger the prime you have, the quicker this goes. So, for 5, 27 divided by 5 is 5 plus something. So 5 of the numbers from 1 to 27 are multiples of 5. We take 5 divided by 5. One of them is a multiple of 5 squared. That means the exponent of 5 is 6. I think we can kind of talk our way through the rest. Of the numbers from 1 to 27, how many of them are multiples of 7? So 27 divided by 7 is, right, 3, because in fact, 7, 14, 21. Okay, so 3 of them are multiples of 7. How many of them are multiples of 7 squared? Again, if the number you get in a certain round is less than the thing you're dividing by, you're done. So you take 27 divided by 3, you get 3. Since that number is less than what you're dividing by 7, you don't have to go any further. So this would just be 3. In other words, 7, 14, 21 all give you one copy of 7. There are no other multiples of 7, and none of those happen to be multiples of 49. What about 11? How many of the numbers from 1 to 27 are multiples of 11? So 27 divided by 11 is 2 plus something. We just care about the 2, and then you're done, right? So this would be 2. How many of the numbers from 1 to 27 are multiples of 13? Right, 27 divided by 13 is 2 plus, so it's just 2, and then you're done, right? There are no multiples of 13 squared. Again, when you multiply 1 through 27, 13 is a multiple of 13, 26 is a multiple of 13, that's it. How many of the numbers are multiples of 17? Right, just 1, and in which case you're done. And since this list, these exponents can never pop back up again, once you get a 1, assuming you haven't added any primes at the end that don't belong, what do these numbers have to be? They're also going to turn out to be 1s. So there's the prime factorization of 27 factorial. In other words, if you've never seen this before and you're not sure sort of what the gimmick is or what the idea is, it can cause problems. But once you see how to pick out the number of times each prime occurs, it's pretty straightforward. I mean, there's always room for computational mistakes, but it's pretty straightforward. If your calculator has, I don't know if you can really double check your answer on the calculator, because if you multiply this out on your calculator and you multiply this out on your calculator, it's probably going to start rounding off at a certain point, so you can't check all the decimal places. So, any questions on the factorization of 13 factorial and 27 factorial? Now, for 12, you wanted to know how many zeros occur on the far right when we expand out 1,000 factorial, 200,000 factorial, and 500,000 factorial. And to start, what we can notice is, let me write down the prime I'll just make up the prime factorization of a number, and we'll see how that applies to this particular problem. So suppose I have 2 to the 9th, 3 squared, 5 to the 14th, and then other primes I'm not going to worry about. So there might be 7s, 11s, 13s, who cares? Okay. What causes a 0 to be at the far right of something? In other words, if you multiply something out, or if you have a number and there's a 0 at the far right, that means you can factor out what? You can factor out a 10. So, but in terms of prime factorization, factoring out a 10 is the same as factoring out one copy of which 2 primes? 2 and 5. So, if you have a number, what you're really saying is how many times can I pull out both a 2 and a 5? Well, if I want to know how many times I can pull out both a 2 and a 5, I look at the prime factorization, I look at the exponent of 2 and the exponent of 5, and I take the smaller one because that's the one that runs out first, right? So for this particular number, I could pull out 9 copies of 2 and 9 copies of 5. So this would be 10 to the 9th. Again, that's not a prime. And then what's left is 3 squared, 5 to the 5th, and other stuff. But since you've run out of 2's here, there's no way that this product here is going to end up in a 0. So all the zeros come from here. So if you have the prime factorization of any number, not just a factorial, if you have the prime factorization of any number, if you want to know how many zeros at the end, that's the same as how many times can I pull out a 10. And where that comes from is you look at the exponent of 2 and 5, and you take the smaller one. So far, so good? Now, if you happen to be looking at a factorial, which is from Michelle's question, if you look at a factorial, as you go down the line, the exponent of 2 is always going to be greater than or equal to the exponent of 5. In fact, I was probably being too conservative. It probably was going to be strictly greater than the exponent of 5. But the point is, 5 is never going to have the bigger exponent. Which means if I'm looking at a factorial, the only thing that I really need to compute is the exponent of 5. Because the only thing that matters are the exponents of 2 and 5, and I need the smaller one, and 5 is always going to have the smaller one. So if I'm looking at 13 factorial, it's going to have 2 zeros at the end. Because you can pull out 2 copies of 5, and you can certainly pull out 2 copies of 2. There are plenty more 2's around, but then you can't get any more 10's to pull out. For 13 factorial, rather for 27 factorial, you can pull out 6 copies of 5. You have no trouble also pulling out 6 copies of 2. But once you've pulled out the 6 copies of each of these, there are no 5's left over. So that would mean there are 6 5's, or rather 6 zeros at the end. So there's the technique. Now we just have to apply it to these specific numbers. So for number 12, what was the first factorial that we wanted? 1,000 factorial. So the only exponent we really care about is the exponent of 5. I mean, we also care about the exponent of 2, but we know the exponent of 5 is going to be the smaller one. So we really only have to compute the exponent of 5. So we do the little trick. Take 1,000 divided by 5. That says 200 of these numbers are multiples of 5. But then we take this one and say, okay, how many of these were multiples of 5 squared? 40 of them. But of these 40, how many of these were multiples of 5 cubed? Just 8 of them. Well, of these 8, how many of them were multiples of 5 to the 4th? Just 1 of them, again, plus stuff. And then you're done. So again, if you look at all the numbers from 1 to 1,000, every 5th is a multiple of 200. They give you a 5. But 1 out of every 25, or 40 of them, also is a multiple of 25. But 1 out of every 125 is a multiple of 125. And since 5 to the 4th is 625, 1 out of every 625 is also a multiple of 5 to the 4th. So each of these gives you a factor of 5. These give you an extra 1. These give you yet another extra 1. These give you yet another extra 1. So when you add up the numbers 248 and 1, we end up with what? 249. So exponent of 2 is going to be a lot bigger than 249. This is the one we care about. In 1,000 factorial, 249 zeros at the far right. Again, if you've never thought about this before, not quite so clear, but once you get the idea of what the technique is, pretty straightforward. Questions? So what were the other numbers that we were looking at for this one?
200,000 factorial.
Okay, 200,000 factorial and
5 million.
well, these might look kind of intimidating, but the point is you just have to keep dividing by 5, and numbers like 200,000 and 5 million, when you start dividing by powers of 5, since the powers of 5 grow rather quickly, when you divide by the powers of 5, things shrink rather quickly. In other words, we're not at this too long. So we start with 200,000. We divide by 5. $40,000 of them are multiples of 5. Of those, 8,000 are multiples of the next power of 5. Of those, 1,600 are multiples of the next power of 5. And again, I'm assuming that you have your calculator for this, so I mean that this isn't too arduous. You just need to do a little bookkeeping to remember these numbers. 1,600 divided by 5 is 320. So that's how many were multiples of the next power of 5. 320 divided by 5 is 64. 64 divided by 5, well, this is the first one that doesn't go evenly. What's the whole number here? 12, so plus. Then we take 12 divided by 5. The whole number is 2 plus. But once you're less than the number you're dividing by, you're done. So all we have to do is add up the numbers, well, these 7 numbers in the box. 48,000, 49,600, 49,920. I'll let you tell me. What's it come out to be?
49,998.
49,998. So 200,000 factorial, that's how many zeros are at the end. Bless you. And for 5 million, I was going to say we've done enough, we can sort of stop. However, it's not too bad because for 5 million, $1 million of them are multiples of 5. Then starting with the 1 million, 200,000 of them are multiples of 5 squared. So at this point, so far, it's 1,200,000. But the reason I said, it's not too bad at this point is because in the previous one, we said if you start with the number 200,000 and start this dividing by 5 process, we saw that you came up with 49,998. So if we took this number and plugged it in here, we're going to get all these. So it's the previous answer plus another 1,200,000. So it's 1,249,998. I mean, frankly, I wasn't looking forward to doing the whole thing at this point for 5 million, but we actually had most of it covered already. So, any questions? Well, to make sure that everything is working, let me stop the recording and start another one.